This is Lisa Brashear for the job interview at San Diego City College. This is for students of Math 252, which is Calculus 3. We're going to discuss constraint optimization and Lagrange multipliers. We'll talk about what they are, why they work, and I'll show you a worked out example as well. What are Lagrange multipliers? Lagrange multipliers are a tool for finding maximums and minimums of a function f of x and y, or f of x, y, z, subject to a constraint g of xy equals c, or g of xyz equals c, and c is a constant.
We use Lagrange multipliers in examples like the following to find the maximum volume of a solid given certain dimensions, or to find the minimum and maximum distance from a surface to a point. There are also many economics examples, like maximizing profit as a function of sales of XYZ products with a limited production capacity.
Now let's analyze, why do Lagrange multipliers work? We're finding the maximum or minimum values of a two-variable function f, which you can see graphed in red, on the set x squared plus y squared equals 1, which is the unit circle. We're looking on the circle projected onto the graph to find the maximum and minimum point. When we're looking in the xy plane, we see the contour lines of the function f. Each of the red lines represents a certain constant value for f. The key observation is that the gradient vectors are parallel at the maximum or minimum point. This means the gradient of f must be a scalar multiple of the gradient of g at that point. By just looking at the contour map, where each one of the red contours or level curves represents a certain constant value for f, we can see that the maximum or minimum of f, subject to the constraint g of xy equals c, the constraint will be tangent to a level curve if there's two variables and a level surface if there's three variables. Here's another example showing why the gradient of f equals lambda times gradient of g. On the left, we have the surface f in blue this time, and the constraint g equals c in red. Now we can see that the maximum of f on the constraint g is at the point of tangency. On the right, you can see the maximum points in green. You can also see the level curves of f. Here is the gradient of f, which is perpendicular to the level curve. And then this is the gradient of g, which is also perpendicular to the level curve. Since both these gradients are perpendicular to the same level curve, we say that the gradient of f is parallel with the gradient of g. This means that the gradients are proportional to a constant. And that constant is Lagrange, lambda, the Greek letter L for Lagrange. Therefore, the gradient of f equals lambda times gradient of g. Let's look at one more example. We have our colorful three-variable function f and the constraint g of xy equals c down on the xy plane. This constraint is drawn on the function f superimposed on f. We can see the maximums of the function f on the constraint here and here. So for values root 2, 1, 2 and negative root 2, 1, 2. And we can see the minimums of f on the constraint g here and here. Now I've added the level curves, or sometimes called the contour lines of f, using different colors to show the direction of steepest ascent of f. Once more, you can see in our fy plane that at extreme values Our level curves or contour lines are tangent to the constraint G. So at this extreme value, which is a minimum, we can see that the gradient of f is perpendicular to both curves. We see that the gradient of g is perpendicular to both curves. Sometimes the gradient of g goes in the same direction of the gradient of f, and maybe the gradient of g is not as long as the gradient of f. But the important piece of information is the fact that they are proportional. So we write the formula. Gradient f is, well, not equal to the gradient of g, not necessarily. There's no reason why they should be equal, but they are proportional. So there has to be a proportionality constant, and that is the Lagrange multiplier. Before we do an actual example, let's review the method we will be using. Suppose that f of xyz and g of xyz are differentiable and the gradient of g is not equal to 0. To find the local maximum and minimum values of f subject to the constraint g of xyz equals c, if these exist, find the values of xyz and lambda that simultaneously satisfy the equations the gradient of f equals lambda gradient of g and g of xyz equals c. For functions of two variables, the conditions are similar, but without the variable z. Recall that the gradient is a function that takes in a point in 2D space and outputs a 2D vector. So the gradient is the partial derivative of a function with respect to x, then respect to y, and respect to z as first, second, and third. Another way of writing this is the partial derivative with respect to x, partial derivative with respect to y, and partial derivative with respect to z. To find the gradient of g, we do the same. We take the partial derivative of g with respect to x, the partial derivative of g with respect to y, the partial derivative of g with respect to z. Again, this is the same thing, just written in a different form. Now to solve the equation, gradient f equals lambda gradient g. So we set up the equations. Partial derivative of f with respect to x equals lambda partial derivative of g with respect to x. And then the second equation, partial derivative of f with respect to y equals lambda times partial derivative of g with respect to y. And then same thing for z. Now there's three equations here and three unknowns. So we need a fourth equation. The fourth equation is the constraint itself. Now we set up our system of equations and we can solve. Let's take a look at some examples in the next video.